Okay, anything you want to ask, Rini?
Hello?
Yeah, hello, anything you want to ask?
No.
Okay, if not, let's carry on. Okay, 17.2 in your syllabus, Faraday's and Lenz law. Okay, let's look at the experiment. There's your, basically we a coil of wire. This is probably a cardboard tube. And then there's your galvanometer. There's your magnet we push in. To verify Lenz law, that's the experiment. Set the coil in series with the galvanometer. There's your coil. There's a galvanometer all in series. Push the pole into the magnet. This is a non-pole. A south pole you push in, or it can be a north pole. Do you observe the current in the circuit, right? Especially this part there. The induced field for the coil repels the magnet. So what will be the pole for this part? Yep. What will be the pole for this part? You want to push in the magnet. What will be the pole here? Yep. What's the magnetic pole here? At the right side of the coil.
Ask again, teacher.
What is the magnetic pole here? This right side of the coil here. What pole is this one? North pole or south pole?
Oh, not pull.
Huh? That's
Not
your
pull,
SPM
not
work.
pull.
That's your SPM work. Then to push in the south pole, you want to oppose, so it must be a south pole. Right? So that's why the current flowing is that way. Right? Yeah, remember when we study magnetic, we use a grid rule to determine the polarity of the coil. So this will be south here. Right? Because you want to repel the magnet. You want to oppose it. So current will flow so that you have a south pole there to repel the south pole. Right? So we use a right hand grid rule. There's a right hand grid rule. Right? And then this is your south pole. So that is how the current will flow to produce a south pole or to produce a opposing magnetic field to oppose this south pole that's coming in. Okay, that's the law. That's your verify or Lenz law. Okay, let's just summarize it. Push a south pole of a magnet into the coil. Current flow in the coil such that the pole of the coil facing here, there's the coil there, facing the south pole is the south. Right? So they show you the current flowing there clockwise. So you want to repel the south pole. The induced magnetic field oppose the direct field. Right? So this one doesn't show you the induced field. The induced field will be south pole. So you'll be opposing this south pole there. Right? So we use our right hand grid rule to determine the direction of this pole. Right? From the current, we can determine this is south pole here. Right? Of course, we want to write Lenz law as a general applying to all situations, not only for this particular situation. Right? We push in, remember, we push in, there's a repulsive force. We push in, there's a force. So there's a repulsive force. So the magnet is moving with a constant speed. Right? Our force oppose a repulsive force, so the magnet moves with a constant speed. Okay, so you want a general statement, push a south pole of magnet into the coil, you got induced current flow in such a direction that the pole of the coil facing the magnet is a south pole, right? Current of flow, so that this is a south pole. Right? So how do we write? An induced current or EMF will be established in a direction so as to produce the effect of opposing field which oppose the change that is producing it. This is the change. Push a south pole in, you're producing it. Okay, so we restate the statement. Lenz law, memorize it.
Wait, go back again.
That's the same thing. Any induced current or induced MF.
No, go back again. I'm serious. Jeff. Okay, so what you're trying to tell me is there's that coil and the thing there with the galvanometer. So you put the magnet inside. I mean, you face south, and then south they will repel each other, right? Am I right?
Yeah.
Sir?
So when you remove
Okay.
it, you pull it out, then it will be, this one will be, want to attract it back, no? You want to oppose, it become a north pole. No?
Wait. I mean, when it about to enter, it's
Don't
they are
tell
trying
me
to
I send you a video you didn't watch. It's all there in the video.
Oh, not yet. What's it? Anyway, sir, because south, I mean the other side is south also, so they repel, right? So basically,
Yes.
right?
Yeah.
They repel. But then when they are further to each other, then they want to attract.
So when you pull it out, you will want to attract.
Why?
Yeah, it's what the law is all about. Lenz law, you want to oppose the current of flow so that you want to oppose the oppose what you are doing. Right? That's why we summarize as the law. It's a bit odd, but that's the law. Right?
Yeah, it's kind of weird.
You push in a south pole, you want to oppose, so the current of flow, so that it's a south pole to oppose it. When you pull out, you want to oppose your motion. You want to pull your magnet in again. So it becomes a north pole, that's all.
Wait. I mean, first they repulse, okay, then they are further. So then when they want to attract back, the magnet become not. Is it?
Yeah, so we have to summarize into a general law that apply in all situations.
This is so odd.
Whether you push in a north pole or south pole, we cannot have just push a south pole, then in this current flow, this is a south pole cannot. Right? It must have a general law. It can be a north pole, or it can be moving away.
Okay.
So we summarize in Lenz law. Any induced current or induced EMF will be established in a direction so as to produce effect which oppose the change that is producing it. Right? So Lenz law is a statement of conservation of energy. Yep. Memorize. Right? How do you know it's transformation energy? Right? You push a south pole, mechanical energy, then we got induced current. So that induced current is your electrical energy. Right? So mechanical energy converted into electrical energy. So that's your transformation energy. Right? The force move in, you got opposing force, so you have to move at constant speed. So you have to do work. So the work is your mechanical energy converted into electrical energy.
Yep.
Okay, the next law is Faraday's law. Memorize it. The EMF induced E is proportional to the rate of change of magnetic flux linkage through the circuit.
So basically, EMF is directly proportional to the magnetic flux linkage. That's
Yeah.
it. Okay.
This one is just a small change in flux divided by a small change in time. Same as differentiation.
Oh, rate of change. So that means it's D. Okay. Now it makes a difference.
Right? Negative sign represent Lenz law. That's all. So usually when we calculate, we don't bother about the negative sign.
A negative sign Lenz law is because of the opposing thing, right?
Yeah, you oppose the motion.
Okay.
Yeah. The EMF will always cause a current to oppose the motion. Right? It's found by Faraday. They will go to England, they will tell you Faraday's law. Go to America, They will tell you it's Joseph Henry's law, so it doesn't matter. As long as you know how to
Okay
use
lah.
it. Right? So they are not in phase. That's the essential thing you must know. They are not in phase.
Okay.
Okay, and then from this formula, you must know if you are given a graph of phi against t, then you just read the gradient to find the EMF.
Okay.
Right? Ways to increase the EMF induced in the coil, right? Increase the magnetic field strength, right? Make the magnet stronger. Increase the speed, force it faster in. Increase the number of turns. Number of turns like that, each turn will cut the flux. Flux through the coil increases as the magnet moves towards the coil. Remember the magnetic flux density is non-uniform. Far away, less lines. Nearer, there's more lines. As you push in and in, more flux will be cutting the coil there. Right? There's a greater change. Right? So we are just trying to illustrate to you Faraday's law. Instead of memorizing it, that law will summarize for you. Your flux linkage is BAN. Right? Increase number of turns, increase the EMF, increase the area there, increase the number of, increase the EMF, or B, yeah, you make it stronger, increase the induced EMF. You can also increase B by moving it faster. That's the time that you change it. So we can differentiate it if you want to, become dB dt. So it depends on the rate of change of magnetic field strength. Right?
So the magnetic flux linkage and the area you increase it, but then the B is what again? Sorry.
Okay, remember that. A and N constant, that's why we can take it out. Then this becomes dB dt.
Okay. It's a B is the magnetic field, right?
Magnetic flux density or magnetic field strength. Okay.
Isn't that N?
Yeah, N is number of turns.
Oh, okay. Wait, but if you increase the BAN at the same time, that means the E will increase more, right? So
usually we increase one by one, we don't increase all together. You have to make the area bigger.
But if you increase the T, if you increase the time, but you don't increase the BAN, then the E,
usually the time
EMF
is the
will become
speed,
smaller, right?
The time comes as the speed, the rate of change in magnetic field.
Yeah, if you increase the time, then the EMF decreases, lah. Okay.
I just try to explain to you the phase difference. If you write as E equals to K times pi t, where K is a constant, then in this case, as your phi increases, the E increases. They are in phase. Whereas you put a negative sign there, right? As phi increases, E increases in opposite direction. That means it's in the negative direction, if you like. So it's not in phase, 180 degrees out of phase. Right? If you want, you can think of it as your flux is in terms of sine omega t, which we'll study later on. Then this also sine omega t. You have sine omega t, then E becomes minus sine omega t. No, that's why it's not in phase. Okay, we use sine phi t is phi naught sine omega t. You differentiate, you get this one. Right? Differentiate your sine, become cos. The negative is still there. If omega t becomes your omega. Okay, so you can see that this formula and this formula are different. That's why they are not in phase. Right? If it's sine, non-negative sign, then you're in phase. Okay, that's how we draw. Right? This is a cos graph. This is a sine graph. So they are not in phase. If they are both sine graph, then they are in phase. You use more of that in AC. Okay, let's look at EMF in a linear conductor, a moving conductor. There's your conductor that's moving. This is your rail. It's still a conductor, but it's fixed. Right? We call it real. And then your magnetic field is going in. Right? Remember, the cross is going in. The length is between there. That's the length. Right? That's the length. Right? Not the whole length. Right? The length that is where the current enter and the current leave. EMF is induced in the conductor of length L and moving with constant speed, velocity V, and magnetic field B is given by this formula. E equals to BLV. Okay, let's try to derive this formula. Right? Example 17.2. EMF induced in a conductor of length L and moving with velocity V and magnetic field B. Why is the velocity constant? Yep. Why is the velocity constant? Yes, Sweeney. Why is the velocity constant?
Because there's only
We apply a force. Yeah. Then Lenz's law will tell us the current will flow in such a way so it will produce an opposing force. Yeah? So that's your opposing force. That's why it has to move with constant velocity. Both forces are equal but opposite in direction. Okay. So where is your applying your Fleming's right hand rule? Where's the direction of induced EMF or current? Can remember ma, your SPM work. Okay, cannot
direction of
okay, that's the direction of the current. Your same thing, apply your Fleming's left hand rule. Your field, that's your field going in. Your motion, your thumb is your motion. Can your field is going in, field is going in. Your thumb is your motion, you are moving to the left. Right? Remember, look at the velocity. Velocity is your force or your motion. So your current must be going down. Yeah, focus on this conductor, the movable conductor. Don't bother about the other part. Okay. So current is moving clockwise, no? Can right? Fleming's right hand rule gives the direction of induced current. Right? Thumb first finger and the second finger are all mutually perpendicular to each other. So you can either use a vector, right? Vector form. E is a vector. Right? It's a cross product of V cross B. Right? So you want to use a vector product, you look at the plane. Plane is VB. So your hand must be vertical like that. And then you move your fingers to B. Then you know the thumb will point in the direction of E. Right? Your plane is your V and B is this the screen there, V and B. So you put your hand on V, perpendicular to the plane, to the surface. Then you curve it to B. And then that is your E. Okay, that's what this one is showing you. If you don't like to use a vector equation, you can use Fleming's left-hand rule that way. Right? That's your field B. That's your velocity. You're moving the conductor. That's the conductor moving outwards there. So your induced current or induced EMF is coming out. Okay. Can? Either one. Just memorize one way. Can or not? Can or not? Okay, can we go on? Okay, just a note. Right? Remember, the conductor becomes a source of EMF. EMF is the conductor. In cell, the current move from negative to positive. Right? In cell, right? Current move from negative to positive, but outside there is moving from positive to negative. Right? In the external circuit. So the EMF and the induced and the current inside the cell are in the same direction. So you don't have to worry. EMF and the current in the cell are in the same direction. Okay, let's now derive the formula E equals to BLV. Suppose the conductor of length L move perpendicular to the field. The field is going in. Remember, L is just PQ. This one slightly out. You move it to the left with velocity V. Right, applying Faraday's law, E equals to minus d phi dt. Right, and remember your phi is just BAN. So in time t, right, this is the area that is covered. Area is just your A. Area is just your length, that length there, and that distance travel x. Right? The distance travel x is just your VT. Okay? So replace the A with VT. You get that. Differentiate that. You get that. Right? So as I said, the negative sign is just to show Lenz law. Usually we are required to calculate the magnitude. We don't bother about the negative sign. Okay? Go back and review yourself if you understand. Okay, apply to this equation. State direction of EMF when the rod is moving to the right. Yep. Where's the direction of EMF? Or direction of induced current? When the rod is moving to the right. This is the rod. Yeah, Srini? Where's the direction?
Yeah, wait 1 minute. So
Apply your right hand rule. Leibniz right hand rule. Why so long?
left hand rule or right hand rule?
Right hand rule, right hand rule. It's already shown you how to do that. It's already given you the answer there. That's your right hand. Your thumb is to the right. Your field is going down, north to south, going down. So where is your current?
Going out.
Huh?
Coming out.
Coming out or going in? Into the
Coming
face.
out.
Yeah.
out of the page.
That one is going into the page. That one is B. That one is coming out. There's the thumb. The second finger is going in. Adjust your
That doesn't look like going in, look like going out.
going in, not going out. There, it's going in. You use your finger and try and see. There's your feel going down. There's your thumb there. Yeah. There's your feel going down. Right? The thumb's very difficult to, that one is going that way. So the current, this current is going in. Okay?
Okay.
Okay. Can practice it at home. I'll send it to. Okay, let's go review some of your sinusoidal graph. This is your sine graph. A sine x. Usually for physics, we replace the angle with omega t. So in this case, 1, the A is 1. No? There's a 1 there. So you put A, then replace the 1 with the A, and then this becomes minus A, this one. So we must know the properties. Right? Radian, half pi is 90 degrees, pi is 180, 2 pi is 360, and note sine 90 is 1, 180 is 0, sine 270 is minus 1. Right? There's your cos graph. Amplitude there is 1, so that's why you got 1 here. Right? Cos 0 is 1, cos 90 is 0, cos 180 is minus 1. Right? So in this case, your amplitude, your A is 1. Okay. Okay, electric generator question. Where's the direction of the current? Yep, direction of the current. Concentrate on one part. Can direction of induced current? Well, learn to read. If you take this magnet as inside, this is outside. This one is from left to right. And you can draw the picture here. Right? The field is coming out. Right? This is N is inside, this is outside, this is coming out. Then look at the current. In generator, the coil
The magnetic field is going to the right.
It's up to you, whichever. Right? In generator, the coil is caused to rotate at constant angular velocity. So when you turn it, mechanical energy, you got electrical energy coming out. So mechanical energy convert into electrical energy. So if that is your field, B, right? Up to you to decide which one is right, which one is right, which is in, which is out. So I choose this magnet is in, this is out, so the field is coming out. So that side, the force is going up. This side, the force is going down. Okay, so if I concentrate on this side, field coming out, force is going down. Then that is the direction of my current, clockwise. Can? Yep. If not, look at this picture. Learn to read. Right? It's up to you to read how you read it. You can consider that this is going inside, this is outside, this is left, this is right. Up to you. It's your choice, but you must learn how to read. Okay, can get the direction? This one is means left-hand rule. Remember, it's the field, and then you got a motion, you produce a current. Okay, we are running out of time. Okay.
Okay. Next class lah. Cik. Hello.
Yep. Can.
Next class lah. Cik.
We'll finish it rather than leave it halfway.
How long? How much
We may
more?
have to take another 10 to 15 minutes.
Okay.
In AC motor, the AC supply, that's your AC supply, the part there, now written down, provides the alternating current. Right? That's the alternating current, which is the next topic. The current will flow into the coil, so the coil will rotate. Right? Armature. Right? Armature usually is the coil, but usually the coil is supported, that's why it's called armature. Rotates, the flux changes as the area. Remember, this area will be parallel to the field. But as it rotates, the angle changes, the area changes. So in this case, electrical energy converted into mechanical energy. Okay, let's draw this rectangular coil, rotates a constant angular velocity omega in a magnetic field B. Sketch a graph to show how, assuming the coil is horizontal initially, how the flux linkage varies with time and the induced EMF varies with time. Okay, imagine 3 dimension. This is horizontal coil. Okay, at time t equals 0, flux linkage is BAN 0, right? No area. If you look from the front view, then it's just horizontal like that. And after that, it rotates to vertical. Right? The field is passing through, so this is full 1/4 of the period, 1/4 of a cycle. So here the flux linkage is maximum. Then another quarter, right? This is vertical. This one becomes horizontal again, except the X and Y change, that's all. So this is another quarter, which is half period. So this is 0. Right? So we can draw that. It's a sine graph. Right? Remember, it's phi naught sine omega t. And then omega is 2 pi f. That's your last semester's work. And then EMF induced is just a gradient of the phi versus t graph. That's all. Right? You don't want to differentiate. You just take the gradient. Take the gradient. This is 0. That's why 0. This is maximum. Right? It's there. Right? This is negative. So it becomes positive. And when we look at phase different, we look at the peak, or we look at these 2 points, 2 equivalent points, right? Either the crust and the crust, and see the angle, read this in terms of angle. So we got 90 degrees. From here to here is 90. From here to here is also 90. Okay, you want to differentiate, then you use Faraday's law. Differentiate your sine omega t, we get minus phi naught cos omega t. So that becomes the amplitude. Right? Your E naught equals to phi naught omega. Okay. Right? Remember the E naught, that one, the maximum amplitude depends on omega. If you increase the frequency, you increase the amplitude. And the induced EMF is proportional to omega. And if you look at the graph there, right, you got maximum EMF induced where the flux is 0. Same here. Right? This is maximum. This is minimum. Right? It's still maximum in terms of magnitude. The flux is 0. So when the flux is maximum, EMF induced is 0. Right? That's the point to note. Right? Here, if you don't bother about the negative sign, then you get one is a sign here, induced EMF, one is your flux linkage. Right? Don't worry about the amplitude, because both are all different graphs. Right? And then remember your math formula. Right? Sine A plus B is sine A cos B, sine B cos A. And if you got cos theta is just your sine theta plus half pi. So compare this one and that one there, that's your half pi. That's where we get your phase difference from, half pi. Okay, why is the induced EMF maximum when the coil is rotating from horizontal position? Right, horizontal position, remember the forces acting, one is up, one is down, it becomes a couple. So the torque is maximum. Right, torque is maximum. And as it rotates, it decreases. Maximum torque and decrease as the coil rotates. So that's why you got your maximum EMF. Okay, that's what this graph just represent to you. Horizontal induced EMF is largest. Maximum flux EMF is 0. Okay, same thing here. Yeah, it's just a minimum, that's all here. Okay, where is the uses? This is just extra point you can just go back and read. Right? Where you have a metal there, this is your pendulum swinging through. We can apply Lenz law. Right? It's very fast, it will stop. Why? Because where it swing, right? You have we call eddy current. Rapidly decrease in amplitude. Why? Because you got induced current. So induced current, it means that your mechanical energy is converted into electrical energy. So the mechanical energy becomes smaller. So the induced current, we call it eddy current. So the energy is dissipated in the metal. That's the reason why the pendulum, after swinging a while, it stops. Right? As I said, these are just for your extra knowledge. No need to bother about that. Right? Eddy current is the induced current. And if you feel slot there, right, you reduce the eddy current, it cannot flow, then the oscillation will last longer. Right? We can call it this or can call it slots there. Right? So we can use this idea in mechanical brake. Large current can pass through a conductor, and electromagnet used instead of permanent magnet to enhance the braking. Right? In this case, this is just an illustration that is made of metal rotation. Right? So if you have a magnet there, then you will stop very fast. So we can use in your electric train where it is moving very fast. And when it's moving very fast, the induced EMF is very, very large. So it will stop faster. Of course, we cannot use it in your car. Reversing to park a car because the car is too slow. Okay, I think I will stop here and then we will do some example. We will look at transformer. Later on, the uses of Faraday's and Lenz law in transformer. Right, so all this formula we have more or less summarized there. Okay, so all these are summary for you, what we have done. And all this you need to remember. Okay, so we will look at the exercise that I've sent you. Right, maybe I'll give you some exercise to try out first. Okay, I'll stop here. We'll still take about 10 minutes to do some exercise.
No, just Saturday lah, just Saturday.
Say
I
again.
want to Saturday lah, just.
10 minutes only, huh?
No lah,